All right, today we are starting section 7.3. We are going back to our similar triangles, but this time we will talk about similar right triangles only. And we will go back to using the idea of an altitude, which you might recall is also the same as the height of a triangle. It goes from a vertex and makes a right angle with the other side. To warm up, are the triangles similar? If so, give the reason. Anybody decide if these triangles were similar, Deidreana? Very good. Yes, these triangles are similar by angle-angle similarity. The way they have them labeled, we would need to know the third angle of one of them, but we could easily figure out this missing angle is 30 degrees if we take 180 minus 80 minus 70. So then, yes, at least two of the angles are congruent. Questions about warm-up 1? Okay, on warm-up 2, we are asked to find the value of x. Which little equation formula is going to help us out with that? Okay, a squared plus b squared equals c squared. That came from our friend named... Right, so his name was Pythagoras, but his theorem was the Pythagorean theorem. It's not very nice. Back in ancient Greece, I'm sure that was a beautiful name. All right. What are you plugging in for A? And for B? And for C? Okay. X has to go in for C. A and B, you could have flip-flopped them and it would have been fine, but you have to use the hypotenuse for C. 14 squared. 48 squared. 2,304. Okay. I don't have that one memorized. When we add them together, 2,500. And then in order to get x all alone, square root both sides. We get 50. Which means that these side lengths are a Pythagorean triple. They're actually the second multiple of a 7, 24, 25 triangle. That would have been in our notes a couple days ago. Questions, concerns, need more time with the warm-ups. Bless you. Okay. If the altitude is drawn to the hypotenuse of a, bless you, right triangle, then the two triangles formed are similar to the original triangle and to each other. Now, I'm going to be a little honest with you. When we set these up, it can get a little confusing. So let's walk through this first one slowly. We're going to, first, let's just name our big triangle. What do you want to name it? CAB. Okay. So let's just have a name for our big triangle. If you want to put under that, that's the big one. You can. We're going to drop an altitude to the hypotenuse, which means we're forming a right angle down there. This theorem states that now these two little triangles that were formed are similar to each other and to the original triangle. So we're going to make an extended similarity statement out of this. We will keep doing this multiple times throughout the notes. The tricky part, though, is then knowing which pieces match up to each other. it would be easy to match the right angles up to each other. So if we started with angle C, we started with our right angle, both of these should then start with the right angle. Now, in order to do this, we need to name this point down here. What do you want to call it? We already have an A, B, and C. So we could use D for dog if you want. If you'd rather use X so it doesn't sound like B or C, you can. So we know that if we started this similarity statement with a right angle, the other two should start with right angles. We all on track with that part? Okay. The hard part then comes in with matching up the other angles. And especially with the way this triangle is drawn, it kind of seems like A and B look like they're congruent, but we don't really know that. So just for the sake of this problem, I'm going to say, let's call angle A 60 degrees. So if you were focusing on your larger triangle, that means angle B would have to measure what?
60 degrees.
No.
50.
Still no.
40.
If I were to take this away, what would angle B have to measure?
30.
Thank you. Are we all okay with that?
Yes.
So now let's look at our little triangles. If we focus just on the little triangle on the left side, what is the angle up here at the top going to have to be?
30.
Thank you. Which makes this other little angle
60.
Thank you. Now, we don't necessarily have to do this on every triangle, but I want to make sure that we are matching up the correct pieces to each other. So, if for my big triangle, I moved on to angle A, then let's talk about our triangle on the left side. For the big triangle, angle A was 60 degrees, and for the triangle on the left side, angle A is still 60 degrees. So angle A is still going in the middle. Now, in my big one, I ended with B, which was my 30-degree angle. So for my triangle on the left, I should end with C. Notice that the C's don't line up with each other, but that's because the C's have different measures depending on which triangle you're talking about. So that was my left triangle. Now we'll finish naming the right triangle. Okay, we started with the 90-degree angle, then we went to the 60-degree angle. So for the right triangle, my 60 degree is at C, and my 30 degree is at B. Again, notice the C's are in different spots, but they're still similar. If it helps you to put angle measures in, go for it. If you don't need to, that's fine. Usually the angles are not going to be marked. If you want to leave them in there, that's okay. We just kind of made an assumption and went with it. Now, if it does happen to be that these are all 45-degree angles, then you could write different similarity statements and still be correct. Okay, any questions about this theorem or pulling out the three different triangles? All right, let's move on. Identify the similar triangles in the diagram. So this is like what we just did. If it helps you to give angle measures to these different angles, R and S, and the little angles up at T, you can do that. If you don't feel like you have to, that's fine. I'm gonna... What? We don't know that for sure. If you want to say if S is 60, then R would have to be 30, that's fine. I just didn't want us to assume that they were going to be congruent. So you could say S is 80 degrees and R is 10 degrees. We don't know, but if it helps you match up your angle pairs, you can label them with numbers temporarily. Just don't get too attached to them. So let's start with the big triangle. How do you want to name the big one? Somebody commit to it a little louder. TSR? Okay. If you start off your big triangle differently, then your other ones would also be named differently. So then let's talk about the triangle kind of on the bottom, the upside down bottom triangle. We started with angle T, then for the bottom triangle we'd have to start with U. Okay, so TSR, it looks like S was the bigger of the angles that was left, so we would have to go from U to T. And then, of course, R is the same in the big triangle and in the smaller one, so R is the leftover. I'm writing a little too big, so I'm going to move down a line to write my other similarity statement. So now let's move into the kind of top right little triangle. What angle do I need to start with? Good, start with the right angle again. And then we move to the bigger angle, which would be S, and the smaller one is T. If it helps you, reinforce it by putting numbers in there, like 80s and 10s, 30s and 60s. Bless you. You can do that. That's fine. Just make sure you're being careful to match up the correct pieces with each other. All right. Next one, my big triangle. How do you want to name it? Everyone's whispering, so I can't really hear anybody. DEF. Thank you, Micah. Okay. It doesn't really matter how you name your first one. If you want to keep starting with the right angle, that's fine. You could name it EFD, EDF. We're going to go with DEF this time. That was the first one that I heard loud and proud. So if we started with angle D, that appears to be the bigger of our two unknown angles. So if we're working with this top left triangle, I would again start where? D, because it's the same angle as in the big triangle. Then I had gone to E, which is my right angle. So from D, where should I go? G is now the right angle of this triangle. And then, of course, my last letter would be E, the smaller angle. When we switch gears and we talk about the other triangle, the big one kind of on the bottom, which angle is going to be considered the bigger of the two unknowns? E. In the middle we had the right angle, and then the other one is F. Are we getting the hang of how these go? Okay, you pick how you name the first one. I would recommend always starting with the big one, and then name your other two smaller ones. The figure shows the side view of a tool shed. What is the maximum height of the shed? Now this is kind of a two-part problem. We need to identify the similar triangles, maybe more than two parts. Identify the similar triangles. Our goal is to figure out what this altitude is. But is this altitude from B to D going to give us the height of the whole shed? No, we would then have to do what? Add 9 to it to get the whole height. Okay, do we see where we're going with this? If we can figure out BD, then we can figure out the height of the shed overall. So, in order to do that, we are going to use our similar triangles. So this part's not really different from what we've been doing. We're going to make our extended similarity statement. I still recommend starting with your biggest triangle, so that would be what? BAC is similar to, so we started with B at the right angle, so for our next one we should start with D as in dog is our right angle for either of the other two. Let's do the left side, the little one on the left. So we would go from D to where? A is the same exact angle, and then B finishes off that little triangle on the left. Then we're going to name the other triangle on the right side. Again, we start with D, our right angle. Then we would move up to B, and last we have C. Questions about the similar triangles? Yes.
Does it matter what you put the last two in? Like for DAB, AB, doesn't have to do DBA instead?
If you have named your first one BAC, then yes, it does matter.
So how would you know what order to put them in?
So B was our right angle for the big one. So we had to start with D. You're good with that part?
Mm-hmm.
Okay. So then we moved on to A for our big triangle. Well, this angle A is the same exact angle in the big triangle and in the triangle on the left. Does that make sense? They overlap there.
Yeah.
So those had to match up with each other, and then that left C and D to match up in the end.
What about DBC?
For DBC, again, start with the right angle. This time, if we go back to the original, the big triangle, C overlaps. So the C was on the end both times, leaving B to be in the middle. Does that make sense? Okay. So if you want to think about that instead of giving them measures, you could do that. Think about where they overlap for that triangle. That's part of why I would always recommend starting with your big triangle, not one of the little ones. Other questions before we write a proportion? Okay. So we, of course, are going to use our big triangle because we know all of the sides of the big triangle. What is the length of AC? I'm telling you, we know all of them. What is the length of AC here? Okay, that's 17 because they marked it at the bottom. So we do know all the legs and the hypotenuse of our big triangle. If we focus on the triangle on the left side, really you could do either one, left or right. If we focus on the triangle on the left side, the side we know is 8. What is that in just that small triangle? Is it a leg or is it a hypotenuse? It's a hypotenuse. So if I want to compare that little triangle to the big one, I would compare the 8 to, careful, the big one. What's the hypotenuse of the big triangle? 17. Does that make sense? Hypotenuse of the little one to the hypotenuse of the whole big one. Not the bigger half, but the entire big triangle. Does that make sense?
Yeah.
Okay. No? Okay, so you're okay with this being the hypotenuse of that triangle? That means I have to compare it to the hypotenuse of another triangle. You could compare it to the hypotenuse of the other half, the other side, but that's not going to get us anywhere because we don't know anything else about that triangle. So I want to compare it to the giant big whole triangle here because I know all of those sides. So the hypotenuse of the giant triangle is 17. Is that okay? All right, other questions, concerns? Okay. Equals. Now what we're interested in finding is BD, so I'm going to label that with an X. Over. Now we have to decide what we're comparing BD to. This is not as easy as saying hypotenuse to hypotenuse. So what you could do is go back to your similarity statement. And if we look at this little triangle on the left, BD would compare to which side from the other big giant triangle? BC or CB? Which in the diagram the length of CB is 15. Any questions about setting up the proportion? Okay, from there, I think most, if not all of you, would be fine to solve that. When we cross multiply, what do we get? Good. To solve it, we have to, and we would get, okay. And they did not label our units, so we'll just leave it alone. That, of course, does not get us to the answer because we still have to add what? Add 9 to get the whole height. So if we want to know the maximum height of the shed, we would still have to add the 9 to that. So 9 plus 7.05 would be 16.05. And of course, if they gave us units, we could put those on there. I'm guessing it's probably feet, but they didn't tell us. Maybe it's a miniature shed measured in centimeters. Any questions, concerns about example 2? Anybody need more time on this slide? On we go. Example 3 is really pretty similar to what we just did, just without the context of an application. Identify the similar triangles, find the value of x. Okay, when we do this, we should start off by naming all of our triangles. Strongly recommend starting with your biggest triangle. How do you want to name it? GEF. Okay. Of course, if you made a different decision, that just means the rest of your similarity statement will look a little different. G for our giant triangle is the right angle. So either of the next two are going to have to start with H for the right angle. So let's do the little one kind of on the top left. If we went G, E, F, E is where these two overlap. It's also the bigger of the angles. So E is still going to go in the middle. Which, of course, leaves G to be our leftover last angle. Questions about that one? Okay. If you like sticking with the overlap method, if we look at the bottom big triangle compared to our giant triangle, where do they overlap? F is the overlap entirely, right? So F came last, which means F will have to come last again, leaving which letter to be in the middle? G. Or you could label their measures and go about it that way. Hypothetical measures. Now that we've done all of that, we still need to find the value of x. So x is GH. So really you could use either of these triangles because they both have a GH as part of them somewhere. There are multiple correct ways of doing this, is what I'm trying to say. So which triangle do you want to focus on? The little one or the slightly bigger one? Somebody loud and proud. Little one. Okay, so we're going to focus on our similarity statement in the front. It doesn't mean you can't use the other triangle back here. We're just not going to focus on it this time. So we need to be able to compare sides that we know. What's the only side we know from the little triangle? GE, which has a length of 3. Now you could understand that GE is the hypotenuse, or you could just look at look at your GE back here, and that's going to have to match up with what side from the other triangle? So EG back here, this was our small one, is going to match up with EF back there. Are we following? Yes, no, maybe so? Okay, it would be 5 again. So those are both the hypotenuses of their respective triangles. Equals, we're looking for GH, which is X from the little one. And GH would compare to which one from the largest triangle? GF, which has a length of 4. Are we following how I'm setting this up? Okay, this is not the only correct way to do it. You could have taken the reciprocal of both of these, so you could have had 5 over 3 equals 4 over x. That would have been fine. But when we do this, we have to cross multiply. We get 5x equals 12, divide, and we get x equals 2.4. So on the example 2, I think we had to round. This one I don't think rounded, right? It was just 2.4. Okay. So definitely don't round to a whole number unless the problem tells you to. Like on this one, don't round it to 2, just leave it as 2.4. On the last problem, where you probably got a much longer decimal because you divided by 17, it's fine if you had to round it to a couple decimal places. Other questions? We ready to try one more? Okay. Last one is similar to the last problem. We'll start off talking about our triangle similarity. How do you want to name your largest triangle? JML. Okay. Let's name the bigger bottom triangle next. So we started with angle J for our giant triangle, and that's where they overlap. So I would start with J again. M is the right angle for the giant triangle. So the right angle for the one we're talking about now is K, which leaves M as the finisher for that triangle. All right, naming our last one. Which angle are we going to start with? M, and then our right angle is K, and the last angle is L. Okay, if it helps you to label these with hypothetical degree measures, you can do that. Then we need to find the value of x. So you have to pick your big triangle and one of your other triangles. I would recommend picking the larger triangle on the bottom this time, just because that's the one that we went to next. So I'm going to kind of ignore the smaller triangle up on the top. If you want to do it a different way, that's fine. What is the only side that we know the whole thing of for this one on the bottom? JM. So JM is going to get compared to JL from the other one. So what would my ratio be? What's JM compared to JL? Okay, if you would rather have JL on top and JM on bottom, that's fine. You just have to be consistent. The side that we don't know is KM, so I'll put my X there. KM corresponds to which side from my giant triangle? ML. So ML has a length of what? 5. And we can once again cross multiply and solve. This time you probably will get a bit of an ugly decimal. I would be fine if you left it as an improper fraction, but if you want to put it as a decimal, what is it rounded to the nearest tenth? 4.6. Okay, I'd be okay with that. Questions, concerns? Needing more time? Okay, so that is the end of